All right, hello guys. So welcome back to the next video here. So we're going to talk about another concept. So in the last video, we talked about how v, our velocity, is the derivative of position. Derivative of position, which of course is our dx dt. Now, what all the astute students, of course, are asking is, well, what if you took the derivative of velocity? So what if you went one step further and found the derivative velocity with respect to time? So what that is that is my change in velocity over time. And the way, not the way, the name that we have for this is we call this our acceleration. And we write it as a of t. Okay. Now, again, I think it's useful to think about units for these. So the units of a velocity would be in terms of, say, meters per second. So when we think about the units of acceleration, the dv dt, the units there would be, would just be the units of v over the units of time. So that would just be meters per second, or you could put both seconds on the bottom and write meters per second squared. So that's our new idea today. And the way I want you to think about this is not from a physical standpoint, but from a calculus one. So think about this as like an f prime, and an f double prime. So f being our position, f prime being our velocity, and f double prime being our acceleration. And again, the way we denote this is our position, we call that x of t. Our velocity, we call that v of t, which is the derivative of position. And then our acceleration a of t, that is the derivative of velocity, or the second derivative of position. Okay, so that's how we're thinking about those. And again, if we want to think about these three quantities in terms of units, the units of position would be in terms of meters, velocity is meters per second, and acceleration would be meters per second squared, or feet per hour, miles per hour square, something like that. It's the distance over a time is the key measurement there. Okay, so let's talk about what this means. So in terms of like how you want to interpret this, if your acceleration is positive, what that means is that, okay, so if your acceleration is positive, that means that your v prime is positive. So that means that your v is increasing. Right? If your derivative is positive, it means your original function is increasing. So, for example, like the signs could be different. Like v can be positive and increasing. So what that would look like is that's like your velocity is bigger than 0 and your acceleration is bigger than 0. So what that looks like, let me show you a little picture here. I have this dude here, and you can set him to have, say, a positive velocity. So he's walking over to the right. Remember, the positive direction is right. And then a positive acceleration. And what that means is his velocity is positive. Or his velocity's derivative is positive. It's going to keep getting bigger. So we're going to see his velocity. He's still moving over to the right, but that pace is going to speed up. So watch what happens when I hit play. So he's moving to the right, and then he gets faster and faster and faster and faster as we go. Okay. Now, you could also have a negative velocity, but a positive acceleration. So what that would mean is that you had a negative velocity, so you were moving in that negative direction, but you actually had a positive acceleration. So you were moving in that direction, but then it became more positive. So if your velocity starts at -2, then maybe it goes -2, then -1, then 0, then 1, then 2, then 3. So if it keeps increasing, eventually it'll turn into a positive number. So look what happens here. We're going to start with a negative velocity in red, and then the acceleration is going to be positive. So he's going to start watching negative, but then his velocity keeps becoming more positive, and he starts speeding up and going more and more towards the positive direction. Okay, so that's what's going on if you have a negative velocity and a positive acceleration. So v can also be negative and increasing. So if your velocity is increasing, that means your v prime is greater than 0. So your a is greater than 0. If your velocity is negative, of course, that just means that your velocity is negative, so you're moving to the left. And of course, the opposite of this is true, right? You can have a negative velocity and a positive acceleration. And that would just be like, okay, you're moving to, sorry, let's flip that, a positive velocity, but a negative acceleration. So that means you're going forward, but then your velocity is pulling you in the forward direction, but your acceleration is pulling you in the other direction. So you're going, and that's like you're driving forward and then you hit the brakes. You're going forward, but that velocity is decreasing. So in that case, like here, if your velocity is negative and increasing, your velocity is going like, -3, -2, 0, 1, 2. In this case, if you had, for instance, a positive velocity but a negative acceleration, it's like you're driving 60, 50, 40, 30 down to 0. And then eventually you go in reverse. And it would look like this. You're going forward, but your acceleration is pulling you back the other direction because that velocity is decreasing. So anyway, that's just to show you visually what's going on. Again, I think you want to think about these just in terms of f, f prime, and f double prime. Okay, so that's just visually what's going on. Let's do some example problems. So, for example, suppose I tell you that a position is x of t is equal to, I don't know, sine of t plus t cubed minus 3t minus 4. And then I ask you to find the velocity and find the acceleration. Now, of course, you just take two steps, right? You just take two different derivatives. So my velocity would be the first derivative. So the derivative of sine would be cosine of t, and then plus 3t squared minus 3. And when you go a second step, your acceleration, that's the derivative of velocity, right? So you take one more derivative. So you would just get negative sine of t plus 6t. I hate that pluses and t's look somewhere. Anyway, so that's what you're doing, right? You're just taking another derivative there. Okay. So we could go the other direction as well, right? Just like how you can go down this chart by taking a derivative, you can go up the chart by taking an integral. Right? If you integrate acceleration, you get velocity. If you integrate velocity, you get position. So in this next example, let's suppose I tell you the acceleration is equal to 12t, and I'm going to say find a velocity equation given that my initial velocity, given v of 0, oh Jesus, given v of 0 is equal to 3. Okay, so again, I think about this like they gave me f double prime, they're asking about f prime. So my velocity would be the integral of my acceleration function. So that would be the integral of 12t dt. Okay, so now that's an integral you guys know how to do. It's just 6t squared plus c. So what I'm going to do at this point to find the c, I'm going to plug in that 0, 3, that when t is equal to 0, we have a velocity of 3. I'm going to plug in that 0, 3 to find c. All right, so I'm going to get 3 equals 0 plus c. Okay, so my velocity is 6t squared plus 3. Now you can keep going another step, right? So you could say, like as a part B of this problem, if I tell you that x of 0 is equal to 5, I'm going to ask you to find x of t, the position equation. And we could just keep going from here, right? We could just integrate one more step. So my position is just the integral of v, so I'm integrating 6t squared plus 3. So I'm going to get 2t cubed plus 3t plus c for my position. Now again, I'll just plug in that initial condition there, that 0, 5. So I get 5 is equal to 0 plus 0 plus c. So my position function there is 2t cubed plus 3t plus 5. Okay, so that's just going the other direction, right? If you start acceleration, you just integrate a couple steps to get back to that. Okay, a couple other questions here. Let's do a few more. Another one with an integral here. So suppose I tell you a particle has acceleration is given by a of t is equal to 3 minus 6t squared. And then I'll say at t equals 0, my velocity is equal to 5 meters per hour. And then I'll ask you to find velocity at time 2. Now this is a classic example of a fundamental theorem problem because they give you the acceleration, and acceleration we know is v prime. They told me right here v of 0 is equal to 5, and they asked me to figure out what v of 2 is equal. So again, this is a situation where they give you an equation for the derivative and ask for the original function. You have an initial condition, that's the FTC. Right, so I'll say v of 2 minus v of 0 equals integral 0 to 2 of that v prime. Okay, so v of 2 is what we're trying to find. So v of 2 minus 5 equals integral 0 to 2 of this function. Now again, you somehow passed the first semester of this class, so hypothetically you know how to do this integral. It's just 3t. That's 6t cubed over 3, so that's 2t cubed. You can do this on your own, of course. So you just get v of 2 minus 5 equals, plug in the 2, you get 6 minus 16. Plug in the 0, of course, you just get 0. All right, so that's negative 10, and then we add 5, so I got v of 2 is equal to negative 5. Okay, so this is just using the FTC, the fundamental theorem of calculus, to help us solve this problem. Okay, let's look at like one or two more here. So if I give you like a table of data, so they love giving you a table, and they love giving you velocity data. So here is velocity of some object. So we say here's like t in terms of hours, and here's like v of t in terms of, I don't know, like feet per hour or whatever. And the t goes like 0 to 5, and then this goes like, the velocity goes 20, then 30, and then 35. And I'm going to ask you to find, or maybe not find, maybe estimate is a better word. So estimate the average acceleration on the interval from 2 to 5. Okay. So you get this table of velocity to ask for an average acceleration. So an average acceleration, again, acceleration is the derivative of velocity. So they're asking me to estimate the average slope of the velocity on 2 to 5. Well, I don't have an equation that I can just plug in, but if I have this velocity, I can just find the slope from 2 to 5. So, okay, so that would just be my velocity, my average slope of velocity. So that would be like v of 5 minus v of 2 over 5 minus 2. So that would be 35 minus 30 over 5 minus 2, which would be 5 over 3. Now, in terms of units, again, you just think about like what are the units on top over what are the units on bottom. And this is an acceleration, so it would be feet per hour, and that makes sense to me. So that's how you do a problem like this, where you have to estimate a slope from a table. Okay, I want to do like one kind of calculator problem to show you that. So let's say I just give you one more, and we're just going to solve a bunch of problems like this in class. Say so an object has velocity v of t equals 6 minus e to the 0.05 t squared for all t values that are greater than or equal to 0. Okay, and then the initial position is x of 0 equals 2. And then I'm going to ask you to find the position at the time this object is first at rest. Okay, now you can't read this necessarily, or you can't see this necessarily by reading this, but the key is that this is actually a two-part problem. There are two things you need to do in this problem. So find the t when it's at rest, and then the second thing you need to do is find the position at that time. So when it tells you like find the position of time the object is first at rest, your first thought should be like, well, when is it at rest? I got to figure that out first. Okay, well, if it is at rest, what does that mean? If something's at rest, that means the velocity equals 0. So that means that 6 minus e to the 0.05 t squared equals 0. Now, this is a problem which hypothetically you could solve by hand, and you can just take some logs or whatever, but you can also do this on your calculator. So on your calculator, what you could do is you could just graph this and find a 0. So just say, okay, I'm going to graph the left side of this equation and just see where it's equal to 0. So I'm going to graph right here y equals 6 minus e to the power of 0.05x squared. Okay, now they did tell me just t greater than 0, so I'll just start my graph. My x min will be at 0. So when I graph this, okay, so the time it's first at rest is when the velocity is equal to 0. It's that x-intercept right there. So I'll go to second calc 0 to find it. That tells me where the function's at 0. So I'll give it a left bound, I'll go over a little bit, give it the old right bound. I'll just hit guess again. So that gives me the time first. So one thing you want to make sure you write extra decimals here. It's not your final answer, So write as many decimals as you can, probably like at least 5 here. Okay, so that gives me the time when it's first at rest. But now, the problem asks me to find the position at that point in time. Okay, well, my position is equal to the integral of velocity. So that's telling me I'm going to use the fundamental theorem. Because they told me that x of 0 is equal to 2, and they told me this equation for x prime, and now they're asking me to find x of 5.98625. So that problem is just screaming fundamental theorem at me, right? It's just saying like, okay, x of 5.98625 minus x of 0 is equal to the integral 0 to 5.98625 of that x prime equation, which is this velocity equation. Okay, and then I know this on my calculator is equal to 2, so let's just add that over. So that means my x is going to be 2 plus the integral 0 to 5.98625 of your velocity function. Okay, and of course I should have pointed out at the beginning of the problem that this is like a calculator problem, but I'll be very clear about that in your homework, so I won't worry too much about that. Okay, so anyway, we'll just plug this all in my calculator. So I'll go here, I'll just put the 2 in front so I don't forget. So I'm going to do 2 plus, and then I'm going to not hit that button. I'm going to take the integral of, and the integral was 6 minus e to the power of, let's see, 0.05x squared, and then that's with respect to x, and you're going from 0, and I'm trying to find that point when it's at rest, so that's the 5.98625. Okay, and then you just let your calculator do this whole thing, and it'll tell you that position at that point in time is 25.2178. Okay, so again, don't be scared when you see this type of problem. Just say, okay, well, first off, I need to find when it's at rest, and then the fundamental theorem is how I can, once I have that time, is how I can find the position there. Okay, thanks for watching, guys. I'll see you all soon.